Good afternoon, everyone, and thank you for joining us. Today we have Brian Patterson. Brian Patterson is the president and founder of Emerge Alliance. He is a 30-plus year veteran of the electrical and electronics industry, and he has extensive technical and work history in electronics, fiber optics, and building electrical system technologies. Brian helps Solar Power National very much with the smart energy microgrid. He's kind of the engineer and thought leader behind that. With his thought leadership, transforms a lot of that into how we're using energy to and distributed energy resources in the grid. And Brian's presentation today will dive more into a little bit of that. Throughout the presentation, if you have any questions, please be sure to use the chat feature. You can go ahead and test that out, and we'll answer all the questions at the very end of the presentation. So without further ado, Brian, I'll hand it over to you.
Thank you. I'm just reconnecting here. I'm sorry, Greg. It looked like the internet dropped out on me there for a second.
No problem.
I hope you can hear me now. Can you?
I can.
Very good. Okay. Well, let me first introduce today's presentation by just saying a few words about eMERGE for those who are not familiar with us. We are the world's largest professional organization that's advancing the use of hybrid direct and alternating current direct distributed energy resource microgrid technology. And we're really trying to facilitate greater power resiliency, efficiency, safety, and sustainability through maximizing the potential use of clean, renewable on-site energy. We're an open industry association. We collaborate with commercial, government, and academic organizations, and we develop Vanguard standards for commercial, residential, campus, and community use. And importantly, and you'll hear more about this later, we conduct live hybrid microgrid demonstrations and workshops at major trade shows and conferences throughout the year. I'd like to start out by just pointing out that for a long time, it has been known and preached, if you will, that the world's largest man-made machine was the electricity grid. The question is does that still hold true? And some would have it that it does not anymore, that the world's largest man-made machine is now the internet, particularly with the advancing interconnection of devices in the Internet of Things, with now close to 10 billion interconnections around the world. So it looks like the electrical grid is being outdone, if you will, after almost 100 years of holding the lead, if you will. So the question is, what will it take for us to get the grid to catch up, maybe even sprint ahead again of the internet, essentially transforming the grid into a suitable infrastructure for this new age of electricity, and I'll explain more about that. But we really would like to facilitate a system for electricity and do what the internet did for information access for electricity. So that's our real objective. Now today's subject is about the distributed energy resources and their integration into a transactive mesh network. And for this subject, we really want to look specifically at the grid edge. That's where most of the action in DERs will be prevalent. At the grid edge, there are several key drivers that are actually forcing, if you will, a consideration of the change, a significant change at the edge of the grid. Three of the major categories in that vein are there's a lot of new electrification happening, and probably the biggest being in the vehicle transportation area, but also in other electrical device heat pumps and splits and so on. There's also a huge trend towards decentralization. Obviously, the distributed resources are essentially decentralizing the system over time. So we'll talk a little bit about that. And last but not least is the grid is being digitalized or a digitalization of the grid. So we'll also touch on that and what aspects that includes.
Hey, Brian, your
yes.
PowerPoint isn't being shared, just so you're aware.
Oh, okay. Let me see what happened with that. Sorry about that, folks. Let me just go to my Zoom dialog here and see if that works. How are we doing now?
You are good to go.
Okay. Um, I'm not going to go back to those other slides, and they will be included in the recording, which you can view later on. Or if anybody has questions, I can always skip back later in the presentation. In any case, the first area we'd like to explore is this notion that more and more things are being electrified. And as I said before, the killer app there of significant electrification increase has to do with transportation. Essentially, as some people say, the sparks are flying when it comes to electric vehicles, and that's on a worldwide basis. We're actually right at the kind of transitional knee of the curve where we're going to go from that slow growth, initial growth, and early adopter use, and so on, to a mass adoption of electric vehicles. The interesting thing about this is that it's going to happen probably a lot faster than most people think. There have been several forecasts about electric vehicles over the last few years, and each time a new forecast comes out, the curve swings up. And you probably heard more and more activity from the automobile manufacturers about electrified cars, both hybrid and pure electrics, as well as hearing from transportation companies in the mass transit area, electrification of rail and buses and so on. So this is happening at a pretty rapid rate, and it's going to put significant pressure on the electric system or the grid and its associated systems at the fringe. These are real killer apps in the sense that they will provide some new opportunity, even though they are causing and will cause considerable strain on the grid for a while. Those accelerating adoption curves are partly a function of the internet and how things get marketed more quickly today than they have in the last decade or two. And the penetration rate, and as most people call it, the full penetration of a new market paradigm is when it hits about an 80% adoption rate. Hitting 80% is happening a lot sooner than before. And as I said, we're kind of at the tipping point when it comes to vehicle electrification. I like to use Tony Seba's pictures from his book, Clean Disruption. If you're familiar with Tony's a Stanford professor that talks a great deal about energy and innovation. But here's a picture from his book on the electric car or automobile transformation at the turn of the last century. There's a picture in New York City. You see it's all horse and buggy in the picture here, and there is one automobile that's a combustion engine automobile there. And this is Easter Day Parade, by the way. So right on Fifth Avenue, if you're familiar with New York City. There is even a short 13 years later, which is a picture again that Tony has in his book. You can see the transition is almost 100% complete. All the vehicles, same picture down Fifth Avenue, approximately same time of the year, during the Easter Day Parade or shortly thereafter. And you can see there's still, maybe I didn't show it there, but there was one horse and buggy left actually after 13 years. But that's a pretty quick transition considering the significant change from horse and buggy to combustion engine. So I kind of put this together as my theory or my premise or my hypothesis about the future, that the combination of electric vehicles and self-driving vehicles are going to make a similar kind of transformation, probably in a little bit less time. So 13 years to go from horse and buggy to combustion engine. I think it may be 10 years or less to see the same effect in electric autonomously driven cars, or at least electric cars. So maybe by 2027 or going to 2030, you'll be hard pressed to find a combustion engine, or at least a pure combustion engine car that's driver operated. So that's my premise on that. But in any case, I'm trying to make the point that electric vehicles are going to happen real fast. It is a significant demand on, it will be a significant demand on the grid, and therefore we need to start adjusting the infrastructure to accommodate that. Primarily, although there's quite a bit of talk about charging cars in homes and so on, the vast majority of cars don't even have a garage. So the idea that all these cars are going to get charged overnight at home is a little bit flawed in its total thought. So there's going to be a lot of fast vehicle charging stations, and you're going to hear more and more about this technology. Some of you already know that a car takes roughly 100 kilowatt hours to get a full charge for 300-mile distance. And if you do it in a slow charge, that could take you, 5 to 8 hours in what they call a level 1 or level 2 charging. But in a fast charger, which is DC based, that can happen in as little as 15 or 20 minutes. Certainly, you can get up to that 80% level in that period of time. Because as you know, most batteries taper off in their charging rate as they start to get full. In any case, what that also sort of suggests is there may be, if you're going to have to use DC power for charging cars, which is a pretty significant application, it'll be one of the biggest applications of power when you're isolated. It'll be very similar to what we used to consider lighting in buildings or something like that at that level. Certainly in the high teens to low 20 percentile of all energy, of all electricity used. So that also means that there's going to be power electronics and other ways of creating DC power out there. And already there's a discussion at the utility level and at other levels about DC as a service, because much of our usage of power today has transitioned from a natively AC power to DC power to power all of our electronics and our electronically commutated motors, etc. So you might see a kind of a killer app that's going to also have put some pressure on the use of DC power as opposed to AC power in a lot of cases. The second big notion here about change at the fringe is the whole notion of decentralization. So decentralization essentially sort of begs to be accommodated in a more mesh-like structure than in a traditional hub and spoke configuration. So this notion of decentralized resources, and particularly obviously the energy resources, is really pushing us toward consideration of a mesh network, sort of grid of grids. Not all DERs are going to be placed into true microgrids, but many of them will be, and more over time will be actually key elements in full-blown microgrids, either at the building level, the home level, or in a commercial level. So you'll see that sort of mesh network naturally looking to form at the fringe as these microgrids at the building level start to be facilitated. So these microgrids are a way that local DERs can be integrated easily and completely. And we're not just talking about one form of distributed resource here like PV. We're talking about wind, we're talking about hydrogen, we're talking about other technologies of both generation and storage that need to be coupled and be flexible in terms of how they get used and deployed in terms of their energy production and use. So this is sort of the analogy to what happened with the internet, where when personal computers first came out, they were isolated kind of machines. So a lot of these microgrids even will be isolated machines, if you want to call them that, with maybe a one-way connection with the utility, or at best a kind of interruptible connection with the grid that won't necessarily allow islanding or independent use while the grid is in a fault condition or otherwise out of service. So there's going to be a first step where these microgrids start to get formed at the buildings and so on. But later on, or maybe even simultaneously in some cases, and there are already tests and pilots underway for this, where they'll be interconnected together in mesh networks and what we'll call community microgrids or neighborhood microgrids, et cetera, just like a local area network was in the computing world. So it's your personal computer got networked, and now your personal power producing and using device is going to get networked, we believe, very quickly in the future here. Those microgrids, in order to be networked into a grid of grids, importantly need a couple of attributes that aren't normally talked about. One is the notion that there needs to be a transactive mechanism at the interface between these microgrids and other microgrids or the grid itself. So that's a new requirement that is being actively worked on by lots of folks in terms of how to manage this, I'll call it arbitration of power in the balance of supply and demand between loads and local producers, prosumers, and so on, and bulk grid and or other neighboring microgrids. But it becomes, the microgrid still becomes that basic node of transactive, of the transactive Enernet. It's internet of power, if you will, through these transactive meters. So it's a little bit like the router that you have in your internet right now that kind of routes traffic in and out of your computer and keeps records, if necessary, of the transactions and so on. And we'll talk a little bit about how that gets accomplished in a bit here. So one of the types of nodes, sort of like a personal computer, in this case a personal power station, is your home. I call this tier 1 because it's like the personal computer. It's right at the base, if you will, of the distributed resources and use of power. And it is the first tier or bottom tier of the Enernet, the energy network. It has all the features of loads and storage, as well as generation capability, et cetera, et cetera. And we're going to see a great diversity of how this gets implemented at the individual home, depending upon economic conditions and depending upon the location of these residences, and a lot of other factors will determine how effective the individual building or residence is going to be in terms of achieving a balance in the energy network. In any case, there will also be commercial nodes. Some of them will be commercial buildings like office buildings. Some of them will be what we call technical microgrids like data centers, central office, telephony, cell towers, cable front ends for the media industry, the cable industry, et cetera. Some of it will be factories and warehouses, which have different power densities and different needs, and so on. But all of these commercial nodes that are going to be capable of managing and producing and storing power will become part of that tier 1 of the Enernet. They're just larger power stations, if you will, power stations and consumers. Now, if you go up the next level, when you start to interconnect these things, you interconnect homes, we typically start to call them neighborhood or community microgrids. So this is very analogous to a local area network in computing. It's the second tier, if you will, of the energy network, of the electricity Enernet. And it simply means that power that's generated locally or stored locally is best used locally, and therefore will first try to provide services and create value at the local level before it gets added back into the bulk grid and so on. And we'll talk about some of the business models that are available there and how that is going to progress over time. The same is true of course, the commercial buildings and and industrial buildings and so on that get included on campuses in many cases, or in industrial neighborhoods in an area. But these, again, are local area grids in the second tier, where you start connecting factories and other buildings that can share power. Some buildings have very low power density, and will be able to accomplish a net positive energy production over their own specific use. And some of them will be still running negative, meaning that they'll have to import power, at least for a good part of their use. Now, at the next level in the bulk grid, there are also microgrids that utilities are deploying for lots of grid support and other just pure green production of power, solar farms, and some power storage and other devices at substations, wind farms, of course, being very strong contenders for low-cost energy, and hydrogen fuel cells, replacing some of the combustion engines at peaking plants and so on. So I call this tier 3 because it's up in that bulk power. It's more the wholesale portion of the energy market, and we'll have probably a whole different set of protocols for transacting power on and off the grid, as it does today, even in the hierarchical kind of configuration that the current grid is in. So tier 3 probably undergoes the least amount of change, but tiers 1 and 2 are where all the, at least in terms of numbers, all the activity is. This grid of grid ends up to be a combination of all those things when you connect it together, with a transactive capability at each tier. So you have peer-to-peer transactions within your tier, and then you have tier-to-tier transactions, which tend to be more in the bulk power, or more in the normal distribution terms that people think of in medium voltages and so on. So this transactive multi-tier Enernet ends up being manageable because you're really not asking the bulk power provider to manage the resources at the fringe, nor are you asking the fringe people to accommodate exclusively the bulk power requirements of the bulk grid. So each tier has its own modus operandi, if you will, and the only difference is, and like the internet, there are points of exchange between tiers that are managed to specific protocols. So that's the way we see that happen. Now, digitalization is the key to a lot of this. It seems like it's going to add a lot of complexity in a sense, but the complexity is being invited in two ways. One is just within your own building, home, or your own tier, let's say. There's a desire to articulate power more precisely and carefully, and so on and so forth. So there's a certain demand for complexity there, but also the fact that you're going to transact between layers adds a level of complexity. But by keeping these two things kind of separate in a way, the tiers can evolve at their own rate. Like smart homes don't have to wait for tier 3 transaction protocols or even tier 2 protocols. They can go and progress on their own. The medium, the tier 2 community microgrids can start to progress on their own without waiting for all smart buildings to be the same, or all bulk power distribution to be the same. And that's the way the internet went, that by having tiers and only having to negotiate the protocols in the exchange between tiers, each layer could progress at its own rate of commercialization and technological advancement. So digitalization really takes two forms. One is the actual digitalization of power itself, and the second part is what we'll call the digitalization of power management, and that's more the analytical and control elements. But in any case, they both are important in this forming of a network grid of grids over time. So what the two differences are, digitalization of the actual power suggests that there is going to be a greater use of direct current power electronics, as power electronics today are paving the way for the use of direct current, and not always having to go to what we'll call the historical common denominator, which was alternating current. Because we know that there are some advantages for alternating current, but there are also disadvantages when we have to do conversions back and forth. And we're not saying that it's going to be exclusively direct current or exclusively AC, alternating current. We see very much a mixture of the two, depending upon where you are in the system. But more and more, I think most of the DC activity, at least initially, is going to be at the fringe. There may be some at the very high voltage DC for long haul transmission from the utility microgrids, if you will, that tend to be natively DC power producers. But by and large, the middle of the grid is going to still operate almost exclusively on AC power. So there are still conversions necessary, but the trick here is to make those conversions as few as possible, and typically at the higher voltages and currents, because they're less overhead, less parasitic, if you will, in terms of loss. So a lot of digital electronics coming in, both in the portable and fixed loads. We're seeing many more electronic appliances and so on with smart controls, and that will be adaptable to non-synchronous bidirectional integration. So it makes the use of DC as a common bus easier to use in a bidirectional integration in this way, and to provide added reliability and safety. And I'll talk a little bit about that, because I think there's a great opportunity coming with digital power that's going to make electricity even safer than it's been before. So today with DERs, we use traditional coupling techniques, which we'll call AC coupled or hybrid solar storage coupling, which essentially involves inversion of the power back and forth to provide the DC power for the storage and the AC power for the uses. It is the easiest way, perhaps, but it isn't always the best way to do things. And I say easy in the sense that AC power is well known, and there's a lot of equipment out there to integrate, even the DC and through inverters and rectifiers. But at the same time, it's not always the best way, because if you can stay DC, if a lot of your equipment, the storage, your devices, and so on, and if you're coupling lots of different devices, you can avoid having to work with the fixed inverter sizes and things like that, and actually stay in the DC mode until you need to use the power as AC, and then you use the inverter at one spot. The simplification of the electronics is rather significant by doing it this way. Now, if you're just integrating one type of DER, it may be a wash in terms of whether you go DC coupling or AC coupling. But as you start to integrate more forms, and particularly as you go into a mesh network, the notion of DC coupling really starts to pay dividends. So we'll probably see a great more about that. I thank Schneider Electric for the case studies that they have done in this area, where they point out, normally when people talk about AC and DC, they right away jump to the efficiency thing. And efficiency is certainly a part of it. And if you do it right, you can probably yield 3 or 4% higher efficiency in a DC system than an AC system that's involving these coupling requirements. However, what's not often talked about is the lower cost of equipment and repair and maintenance, the greater revenue opportunities by doing a stacked value proposition in peak shaving and trough filling and offsets of that type. And as we see more and more, when you couple storage into these systems, there are tax advantages as well. So the stacked value proposition really starts to look a heck of a lot better. And I just suggest that if you're interested, Schneider has some nice information in their case studies on the web, and you can go and see what they say about DC coupled systems. In any case, there is a third option that isn't quite here yet, although a couple of companies are moving down the path towards this, and that's what we call true digital electricity. And that is pulse modulated DC, if you will, that is not constant, but pulsed, and forming, if you will, packets of electrons that can be routed and transformed at each end, the sender and the receiver, just like information is in the internet. So we're probably going to see as we go forward, and like I said, there's already a couple of companies with pretty significant and interesting equipment, not necessarily versatile to do everything and anything in the power system, but in specific applications, it is true digital electricity and has lots of advantages that includes significant safety improvements and other benefits. But in any case, it isn't over yet, and the battles a century ago between AC and DC are yet to be rivaled by perhaps the battles between AC and DC in hybrid systems, and then going to true digital electricity in the future. In any case, the other side of the digitalization of power is all about power management, analytics, the IoT, and the management of devices through registries and service applications in the cloud. What this does is give an intelligence to the electrical system, providing that you can use that intelligence to articulate the use of the electricity, whether it's in speed control on and off, the form of power, the storage levels, et cetera, the choice of sources and so on. That's where digitalization, or the assistance that the Internet of Things brings and the promise it brings to the electrical system. So this is a whole other aspect of digitalization of power management that's moving forward. This is what really powers a lot of the transactive power management. Now, you can still do smart home and not necessarily call it transactive power because you're not buying and selling power. There's no arbitrage or anything else involved. So we're talking about the more advanced use, if you will, a more comprehensive use of digital information and digital devices to provide a framework for transactive power, which means power that can be bought and sold in real time at all levels in the system, whether it's at the retail, the wholesale, or the bulk power levels. What this does is give tremendous capability to all levels, and whether it's a prosumer themselves or a third party or a local service provider or the utility that provides the management for this. Keep in mind that transactive power is not a product, but it's actually a platform. So it's a platform for the arbitrage or the exchange of power in the attempt to balance supply and demand and provide for routing and resiliency and a lot of other factors in the system. So what's the way forward on all this? A lot of people think that this is all about the future and you can't do anything today, but there's a lot going on, and systems are already starting to be deployed. So it's important that you know where it's going so that you don't end up putting in systems that will be obsolete in a short period of time. And I remind people about this and how there was a sort of a rush to efficiency with lighting, and everybody invested in higher tech fluorescent, when right around the corner was LEDs, and there was little or no thought given to how to make the transition forward. Everybody was looking at just improving what was on the table at the time. But by knowing what is going forward, you can look at how you're going to design your products or install your systems so that they are forward-leaning and capable of being integrated into these advanced strategies. However, a lot of this is going to cause disruption along with the opportunity, and a lot of times opportunity is a result of disruption. So I've listed here 4 key areas that I see heavy disruption and yet at the same time significant opportunity. One is in the redesign of regulatory apparatus, the paradigm that we use for regulatory control of electricity. I see an immense disruption in the way we deploy infrastructure and what's going on there, as many of you are involved in that already. I see a redefinition of the customer experience. Simply, you know, most people, as far as power was concerned, their involvement was month-to-month, getting the bill from the bulk provider and essentially managing it simply and on paper. I see a much more active role, although obviously there are going to be third-party systems that are going to allow most folks to sort of have a hands-off and even brain-off kind of system of deploying policies once and then using it, much like the way you manage power in your laptop. In any case, it's going to redefine the customer experience. There's going to be a lot of new opportunities on power production and involvement in the power system. And there's going to be a need to embrace new business models at all levels in both private and public enterprise. So there's lots that's going to have to go on there. Let's talk for a second about the regulatory paradigm. This is probably the most difficult of them all because it is so embedded in our culture to have fixed regulatory schemes. And essentially the ones that used at the utility levels for industry has been essentially unchanged in its basic premises of granting natural monopolies and so on in the regulatory paradigm for more than 100 years. However, there's lots of pressure on the regulatory paradigm to change. And that pressure is going to largely come from an enormously expanded stakeholder base because of the many ways that DERs, microgrids, et cetera, will come into the market through the notion of prosumer and third-party entrepreneurship. Policymakers and regulators are going to have to get together with private enterprise more and more in a collaboration of how to manage that. Much like, again, we did when we went from, I'll call it the hardwired telephone information system to today's internet. Lots of changes in the regulation. We're not, no, I never use the word deregulation except for when I talk about it in a presentation. Because it's really a matter of re-regulating or redesigning the regulatory apparatus, not, you know, opening it up to the wild, wild west kind of environment. But it's a difficult thing to do. It means that policymakers and regulators need to spend a lot more time understanding the new topologies and paradigms and use cases in the electrical energy sector. And a private enterprise needs a lot more to spend a lot more time talking with regulators and policymakers in letting them know how best they see being regulated without infringing on the entrepreneurial aspects of their commerce. So these new regulatory use cases really spring up at the fringe from this kind of notion of peer-to-peer, the peer-to-peer platform of distributed energy resources or distributed network microgrids. So that's where most of the pressure is going to come from to regulators to figure out how to accommodate peer-to-peer, the peer-to-peer market, which is more of a retail market, and to accommodate what we'll call local demand response as opposed to aggregating it in large regions, which gives a lot more flexibility on how demand gets met. And also to local pricing. Local pricing is an important aspect of this because some areas will be more easily accommodated than others to have pricing flexibility. And there obviously be the need for some kind of minimum platform for low income power requirements and things like that. So it's a complex requirement, but at the same time, it's starting to evolve. Regulators particularly in states like California and New York and Maryland, and I'm sure I'm going to leave out people and they're going to yell at me, Massachusetts and other places, have been hard at work already trying to accommodate these new use cases that need to be regulated, but need to also encourage the development of these resources at the local level. The other thing that's going to happen is new infrastructure is required. And if we're not careful, we'll end up with something like this. Believe it or not, this is a real utility pole that I took a picture of just about a year ago in Osaka, Japan. And if you don't think ahead, I guess this is what can happen. Now, that's a combination of electricity and communication utility wires up there. But if you're not careful and really don't think ahead on how all this is going to play out, you can end up with a mess in the public domain. And there's going to be a lot of back pressure not to let things like this happen, or eyesores and eminent domain requirements take over. It's probably going to be more like this, where there may be some secondary links between neighbors and things like that, but not in a significant way if we do it right, where the utility wire today will still carry the most significant loads and so on in distribution to major energy users, and may provide the exchange even at the fringe level. But where that's not possible, or where the links need to be DC instead of AC, there'll be some additional wiring, whether that's done by the utility or whether that's done by third-party providers, et cetera. And there's been experimentation of both. And I know that both utilities and third-party companies have been developing what those links are going to look like and how they'll operate. Because it is not a hub and spoke topology anymore, which means you have multiple interconnects in the mesh network itself. It also means that there's going to be a metering and monitoring activity to accommodate this tiering, where you have both peer-to-peer interconnections as well as tier-to-tier interconnections. So sort of nanogrids, microgrids, and macrogrids all operating in a three-dimensional tiered framework. And this is already starting to evolve. I mean, utilities have for a long time had the two tiers, the transmission tier long haul and the distribution. So we're at least going to add some more into that distribution tier 2. But we're also going to put a whole new layer, I believe, at tier 1. Now, a lot of people say, how are we going to afford that? You know, we can only have, you want to be efficient with your assets and so on. Well, if you haven't looked up recently, maybe your wiring is all underground, which would be nice. But if you notice the utility poles today, at the top, there's still only the 3 wires, but not too far down from that, you'll see a number of wires as you see cable TV and fiber optics and telephony and so on and so forth have populated that, and even wiring into the house and wireless connections into the house have proliferated. Now, if you have the notion that the value of electricity is still going to be a one value for a kilowatt hour, you can look at that and say, wow, anything we do to add infrastructure is going to kick up the cost of a kilowatt. But I can tell you, and from my own experience, and I'm sure yours, on telephony, when we went to new information systems, as long as we provide a new value stack for that additional framework and additional infrastructure, there'll be resources to pay for it. You can't just do the same thing, though, and just add new equipment and new things and expect that people are going to pay just a higher kilowatt hour for everything. So there's going to be an associated need for business models and things to change the value stack in there. The customer experience that we're looking for, I think most people are to adopt some of the virtues of the internet. The internet has this unique ability to be self-organizing and self-healing and therefore more resilient. You really don't have to think about how the information is being managed as kind of a weak transactive cooperation based on protocols and software and so on. It is a bottom-up public structure, although there are still large mainframes involved, banks and financial institutions, insurance companies, and so on. There's a lot of bottom-up. In fact, about 80% of the information on the internet today is created at the bottom in personal computers and personal devices. Only 20% certainly less than 30% is created by central mainframe producers of data. In any case, the presumption that exists in the internet that we're going to want to carry over to the Enernet, the energy network, is that presumption of access equality for each entity. So whether you're producing power on your roof with a few solar panels, or you're running a big nuclear plant, essentially you should have access to the grid infrastructure, whether it's at that tier 1, tier 2, or tier 3 layer, based on the regulatory requirements of each layer. So DERs and IoT and prosumerism are reshaping the industry in this regard. And we're going to want, since we're used to it, the kind of customer experience we get with an integrated user interface experience, where you have a choice of whether you want to be hands-free and mind-free, so that kind of your energy requirements and transactions and all the things that I just talked about are done sort of automatically in a semi-autonomous way. Or if you want active system control yourself and you want to arbitrage power or manage your plant or facility or campus in a unique way from time to time, the user experience should be shaped around the existing kind of internet experience we have. So one of the things that needs to change here in order to get that stacked value proposition that's going to pay for new infrastructure and pay for new equipment and so on are the new business models that will come about. Those business models will break down, excuse me, essentially into two areas: services and apps. And the services can be services to the end customer on the retail level, or to the distributor of power, or to the grid itself. So there's lots of services that will work in both directions. For example, creating virtual power plants, and the value of that versus having peaking plants or spinning reserve and all the other things that the utilities are forced to do today to maintain the power surety. There's things like preemptive maintenance, which once we have a grid where you can actually monitor the articulation of power at that fringe, you can start to do what we do in computing, which is to do predictive maintenance, so we catch things before they go into fault or failure. And then there's apps themselves. There's vehicle charging. There's augmented reality in terms of supporting the grid itself. There's an app that could manage VARs and local peak demand and fault resilience when either man-made or natural faults occur in the system. So there's lots of new services and apps that are capable of financing, if you will, or providing the underwriting for new equipment and new infrastructure. These are the key drivers. Without these, technology for just technology's sake doesn't pay for itself. And as some have learned, even smart grid for its own sake doesn't necessarily pay for itself, unfortunately, until you have a massive fault or something that people can actually put a number on. In any case, that's what's going to pay for things going forward. But that means that there are huge new business opportunities associated with all this, which can be leveraged in this kind of net zero or smart energy marketplace of any energy prosumerism and arbitrage. So the question with all this, I suppose, at the end of the day is how fast is it going to happen and what's the result? But for sure, one result is not what we do with electricity will change the fate of the world, or possibly change the fate of the world. It will change the fate of the world if you take the lead and start to move in the direction that we're talking about. My granddaughter reminded me, she says, "Why are you doing all this, Pop?" And I say, "I'm doing it for you, kid." And she says, well, what, that's really great. Is it going to change my world? And I said, yeah, it's going to change your world. And she says, well, I'm just saying, Pop, I just wanted to know, So in any case, that's what I had to say today about DERs and this grid of grid and transactive energy formation. I would like to acknowledge the contribution of many members of the Alliance and our friends and associates around the world in helping me put this together. So I'll go and ask for questions at this time and see, Greg, if you have any questions that have come in. Greg, are you there? I don't hear you, Greg. Let me check. Let me see if I have anybody on the chat that has a question. If you'd like to, you can access the chat and ask me a question at this point. I do want to speak just for a minute or two about the trade shows that are coming up where we have live microgrid demonstrations and how that all works. So maybe while we're waiting to see if there are any questions, I'll move on to that. We decided a long time ago that one of the best ways to get people to understand what's coming in the electrical industry and in electricity in general was to go to trade shows and really demonstrate the real live operation of microgrids. Over the last year alone, in 2017, we had over 235,000 people who came to look at what was going on with microgrids and how they operate and so on. What we actually do is we operate a real microgrid and power a part of the trade show with the microgrid. And then, of course, we can island it. The next time that we do that is going to be at North America Smart Energy Week, which comes up in September in Anaheim at the Anaheim Convention Center, where is a unique opportunity because Solar Power International is now a multifaceted show and includes Solar Power International, but also Energy Storage International. It includes the Smart Energy Microgrid Marketplace, which is what I'm directly involved in, and also Hydrogen Fuel Cells North America. And I think you're going to see as the years go on that this is not a static trade show where you see the same old each year. That this trade show in particular is one that's really moving at the same pace that smart energy is in the marketplace and continues to reflect the next generation each year. This year's microgrid marketplace will feature, again, a live exhibit of microgrids. We expect to have multiple microgrid controllers operating off renewable energy, powering part of the trade show floor. We also will have some virtual displays of the microgrid at various places around the show, which ties into the educational program at Smart Energy Week, which is really one of the best in the industry at this point in time. The Smart Energy Hall, where the microgrid is, will have its own Smart Energy Theater right nearby. And there'll be special presentations there about microgrids in particular and how they play into the whole notion of distributed energy and the advancement of the Enernet or this grid of grids. There'll also be destination tours, and I'm sure a lot of government and international VIPs have already been scheduled to come through. We will have a grand opening day and a ceremony and a keynote presentation speaker at that time at the show. So if you haven't already signed up or plan on exhibiting at the show, please do so, because I'm sure it's going to be one of the best shows ever. You can see here some pictures. A lot of people come to the show for different reasons, and kind of interesting to discover what we're doing there. We have won the Best Technology Integration Award in the top 100 shows. We demonstrated through a demonstration of the peer GBCI microgrid performance evaluation that our microgrid was capable of achieving a platinum capability, although we're not a permanent installation, so we couldn't get the actual award. But it demonstrated all the requirements for that. And we've demonstrated it at the Consumer Electronics Show, where we powered part of that show. Here you see some of the pictures of the microgrid. We house the active part of the microgrid in an enclosure, a safety enclosure. So we call it the fishbowl because you can't get in there, but you can get to see all the equipment up close, including the busways, the battery stacks, the controllers themselves, some of the monitoring equipment, etc. So it's a fairly complete capability, and you see here the audiences that we house in our theater, explaining what's going on and so on. And let's see.
Hey, Brian, it's Greg.
Yeah.
Just cutting in, and I hate to do this, but we're running short on time here. And we did have a few questions, but I don't think we're going to be able to get to those now. So I saw your comments, Ed, in there. What we'll do is we'll create a page that answers all the questions that we had throughout the presentation here, as well as a page that answers the questions that were asked in the registration process. So we definitely want this to be an open dialogue. By no means, as Brian shows the slide here, we do have another webcast coming up, and we'll send out information on that as well for that August 21st webinar. And if you have any questions, we'll share our contact information, so feel free to reach out to us if you want to learn more about Solar Power International or eMERGE Alliance or microgrids. Thank you, Brian.
Okay, and I think you already mentioned that this webinar will be available for a recorded version of it will be available for people who want to go back over the material.
Great. Thank you, everyone.